Okay, so in the previous video we said that what we need to do is we need to integrate the combination of the positive differential charge element and the negative differential charge element along the z-axis. So what we're saying here is that the electric field strength, the total electric field strength, is going to be the integral from 0 to infinity of this guy right here, which is 2 rho L, I'll just write the dz at the end, over 4 pi epsilon rho squared plus z squared to the 3/2 times rho a hat rho, and this is all integrated with respect along the z-axis with respect to z. So that's the integral that we now have to solve to be able to calculate the total electric field due to these points along the infinite line charge. So this actually isn't too bad. It looks like a really heinous integral, but it's actually not. And that's because 2 rho sub L, 4 pi epsilon 0, rho, a hat rho, none of those depend on z, so they can all just get pulled out of the integral, and I can write 2 times the linear charge density over 4 pi epsilon. Can't do anything with this here because it's inside this 3/2, so this z and this rho are stuck together, but I can pull these guys out, rho, a hat, rho, and now all I have to do is integrate from 0 to infinity of 1 over rho squared plus z squared to the 3/2 dz. And this is a pretty common integral. You've definitely solved this in your calculus classes before. I'll just remind you, not that you need the reminder, but just if you wanted it, that the integral dx over x squared plus a squared to the 3/2 is equal to x over a squared times the square root of x squared plus a squared. And actually, if you remembered that from calculus, my congratulations to you. I had to look that one up. But anyway, this is something that you can usually find in a table of integrals. Clearly, I can just plug that into there, and so we get the electric field strength is just going to be equal to 2 times the linear charge density divided by 4 pi epsilon. I need to multiply that times however far away the point is in the rho direction, and then I need to multiply that by the result of this integral, which is just going to be z over rho squared times the square root of z squared plus rho squared. I need to evaluate that at the limits of the integral, 0 and infinity, and all that has to point purely in the rho direction. So that's the result. All we need to do is evaluate this at the limits of the integral. That's not too bad. All we need to do is plug in the value of infinity for z and 0 for z here. So I'll do that real fast. The electric field intensity is equal to 2 times the linear charge density over 4 pi epsilon times rho times infinity over rho squared times the square root of z squared plus, sorry, not z squared, infinity squared plus rho squared minus 0 over rho squared times 0 squared plus rho squared. And all that points in the rho direction still. So this one's pretty obvious. That goes to 0. This one's a little bit trickier. What we see is that infinity squared plus rho squared is just infinity squared. The square root of infinity squared is just infinity. And so we're left with infinity divided by rho squared times infinity, which is just equal to rho squared minus 1 over rho squared minus 0. So the result of all this is just 1 over rho squared. So total electric field strength then, after we've done our calculus, is 2 rho sub L times rho over 4 pi epsilon times this quantity, A hat rho. We see that the rho here cancels with the rho squared, and we're left with the final form of electric field strength at a point P due to an infinite line of charge is equal to 2 times the linear charge density divided by 4 pi epsilon rho A hat rho. And you saw me scrolling around a second ago. I got a little panicked. I saw a 2 here. I realized for some reason I haven't canceled these and just made this E is equal to rho sub L over 2 pi epsilon rho A hat rho. So this is the final form. This is the electric field strength at point P due to an infinite line of charge along the z-axis. And you just take the charge density of the line, you divide that by 2 pi times epsilon, which is the permittivity of free space. You then find what the radial distance of the point is, and we see that the force is just going to act in that radial distance.